Let's do a different row. Let's do this row down here. Does this row give us all true premises and a false conclusion? Yes, it does. Since it does, that means that this argument is invalid, since there is a scenario, a possible world in which we could have all true premises but a false conclusion. This is like our earlier argument where we said, if it is a duck, it is a bird. It is a bird, therefore it is a duck, or a penguin or something like that. The truth of the premises don't guarantee the truth of the conclusion, and as such the argument is invalid. When it comes time to write out what the values are on your exam or on your homework, you would say that P equals F, Q equals T, and R equals F. And again, we're getting these values by looking at the values over here. Our value bank, our key, our holding block, whatever word you want to use for it, tells us what values we assign to P and Q and R in order to get an invalid argument. Again, this is kind of long, so let's do it a different way instead. The short way. What we do is write down our argument first. So we write down P, arrow Q, P, arrow R, therefore Q, arrow R. Then we want to force the premises and the conclusion to be what we want them to be. We want the conclusion to be false while the premises are true. In this case, we have two premises, so we want both of the main operators of each individual premise to be true. Then we have to ask ourselves, what would have to be the case in order to get those premises to go the way that we want them? Again, I recommend that we start with the conclusion. Let's start by asking, what would make this arrow right here false? We know that an arrow is only false when the antecedent is true and the consequent is false. So now we actually know two of the values. We know that R must be false and the Q must be true in order for this argument to be invalid. And then we want to plug those values in. So we'll put a false here, and we'll put a true here, and then we'll ask the question again. What would have to be true of this premise and this premise in order for their main operators to end up being true? Here's the thing to note. If you were to start with premise 1, it's indeterminate. We can't tell if premise 1, the P, is false or true because F arrow T is true and T arrow T is true. So at least at the start, P is indeterminate with respect to premise 1. However, for premise 2, this is premise 2 right here, notice that the consequent, the R, is false. Remember, if we want a true arrow, the thing that we can't have is T arrow F. We can't have that, or we end up with a false arrow. Since we want a true arrow, that means the P cannot be true. If it were true, we'd have this. We don't want that. That means the P instead must be false. And that tells us that for premise 1, the P is also going to be false. If we want to test ourselves, we can do the following. We could ask, all right, let's check. F arrow T, F arrow F, therefore T arrow F. And then we can check the true values here as well. So for premise 1, F arrow T, that's true. F arrow F, that's true. T arrow F, that's false. Also means now we know what our value for P necessarily is. It's F. When we look at this and we compare it up here, notice that we found the same values. It's just that this was by a process of elimination, whereas the truth table up here was by a process of using the entire truth table. This is sometimes called a truncated truth table, but again, you don't have to use this way if you don't want to. But for a number of folks, it might be simpler and it might be more to the point. What I'm going to do is I'm going to show you abbreviated truth tables for E and F. I'm not going to write out the entirety of the truth tables because that would be a lot. But I'm going to show you the abbreviated versions for both of those, and then that's going to be all for this video. So let's start again by writing out the equation. We have P arrow Q arrow R. That's our first premise. Our second premise is Q. Our third premise is negation R, and our conclusion is P. under each operator for the premise, or for the premises, we want them to be true. The main operator for the first premise is the arrow, so we definitely want this to end up being true. The second premise is a single atomic letter. That means we actually already know the value for Q. The value for Q has to be T. The main operator for the negation R is the negation. We want the negation to end up being true because the negation modifies the R. And we know that for P, we want P to be false. Our conclusion here is also an atomic statement, which means we also know that the actual value for P is going to be false. So we can actually go ahead and start our key right now. P, Q, R, P equals false, Q equals true, and the question is, what does R equal? Apparently I can't draw. So P equals false. Let's go ahead and check, though, by plugging in the values. So let's make P false over here. Let's make Q true. And then for R, we can actually go ahead and figure out what R has to be. In order for the negation right here to be true, that means that R would have to actually be false. But let's check it. Let's see what happens if we plug in an R, or plug in false for R. And let's take a look. F arrow T arrow F, comma T, comma not F, therefore F. Okay, let's figure this out. Well, that's false still. Negation F turns into a T. That's still a T. This would end up false, so we have false arrow false. False arrow false is true. So again, we have a situation in which we have all true premises and a false conclusion. That means that we can affirm that the value that we want for R is F. And that would be enough to answer this question on the exam if you were to get it. Let's look at the last one. The last one is very long because there's 4 letters. That means that if you were to do this with a truth table, you would have a 16-row truth table. That's not nice. Instead, we can do it this way. So this one's a little bit harder in a certain way because we're going to have some uncertainty at the beginning. But let's, at least initially, let's start plugging some values in. We know that we want this to be false. We want all of these to end up being true. Unlike the other ones, it's not as clear-cut at where we want to go from here, but we can still start with the conclusion. Here we're going to posit some guesses at the beginning. Since we see that our double arrow, we want our double arrow to be false, that means that P and S can't match. But that doesn't actually tell us what values P and S have to have. It just tells us that they can't be the same. So for now, let's make P true and S false and see where that gets us. So this is just going to be provisionally, we're going to assume the P equals T and S equals F, and we're just going to see if that leads us to all true premises and a false conclusion. So let's plug in the values for P and S throughout the rest of the equation. So let's make P true here, let's make S false here, and let's keep going. So let's come back to this first premise. Well, if the thing here overall is true, and we know that P is true, that means that the negation Q has to end up being true. If the negation sign is true, that means that Q initially must be false. So provisionally, let's assume that Q is false and plug it in over here. We assume that Q is false. We see that this is true. That means that negation R overall has to end up being false. Since the negation is modifying the R, this is what is false, and it means it flips the value of whatever R is. That means provisionally, let's assume that R is actually true. Let's plug in that value for R. We see that R is true. We've already assigned F to S, but there's a negation right here. The negation modifies S, and it flips its sign to T. Notice we wanted it to be true, and we ended up with 2 t's. So this assignment does work, but let's go ahead and double check it by writing it out a little more assertively. So t double arrow, not f, comma, f double arrow, not t, comma, t double arrow, not f, therefore t double arrow f. Well, that turns into a true, that turns into a false, that turns into true, and let's go ahead and check the value that we end up getting out of the biconditional double arrow. Well, that's true, that's true, that's true, and again, they're all true because they match. And then finally, for our conclusion, that's false because they don't match. As such, we can assign P, Q, R, and S the following values. P, values T, S is F, R is T, and Q is F. Now, this actually isn't the only value that would have worked. Let's scroll up for a second. When you look at this, if you had switched these around, so like if you had put P as being false and S as being true, you would have ended up with a different truth value down here. You would have actually ended up with false, true, false, true. And that also would have been a proper answer to this question. But because of the way that it worked out here, this is the answer that we got. And that would have been an acceptable answer on homework if this was a homework question or on the exam. In this video, what I've gone through is I've gone through a few different ways of doing truth tables to analyze validity. While we did propositional truth tables earlier, these were argumentative truth tables. We wanted to know whether or not an argument was valid or invalid, and for the sake of this class, we only are giving you invalid arguments and asking you to give us what values the different parts, the different pieces, the different P's and Q's and R's would have to have in order to make the argument invalid. In other words, to make the argument have all true premises but a false conclusion. To do this, you can either use a rather long truth table and find a row, find a set of values that gives you all true premises and a false conclusion. You do this by looking at the rows and finding a row that has all true premises and a false conclusion, or by doing an abbreviated truth table. An abbreviated truth table is kind of a logic game. It's working backwards and figuring out what pieces you want at the end and figuring out what pieces you would have needed in order to get there, and it can be a lot shorter. For some folks, though, it might not work. If you're not quite sure how to do the abbreviated truth tables, stick with